This is the last of our videos from unit number 1, and we're going to take a look at something called a back titration. So here's the sample problem I want to take a look at. I have a sample of limestone, 2.43 grams. Now limestone is a mix of calcium carbonate and some other minerals. This is then going to be added to 100 milliliters or 100 cubic centimeters of hydrochloric acid and allowed to react by this reaction, and it's already been balanced for you. In the morning, 10 cubic centimeters of the remaining solution is further titrated with NaOH. We have to determine the percentage of calcium carbonate in the limestone. Let's look at some of the issues with this. First off, that mass of 2.43 grams, placing it here under calcium carbonate wouldn't be correct. The problem here is that 2.43 grams is a mixture of calcium carbonate and other minerals. So we really don't know what the mass of calcium carbonate is, simply that it's less than 2.43 grams. Another issue we have is with the volume and concentration of hydrochloric acid. That was the amount that was added, but not all of the acid reacted in this equation. Some of it was left over to react the next morning with sodium hydroxide. So the problem with using the information for the hydrochloric acid is it's the excess reagent. We need the limiting reagent. Let's take a closer look at what the job of the acid was. Now, that acid essentially had two jobs. First off, I'm going to determine the moles that I actually added. By using that concentration and volume, I used 0.05 moles of hydrochloric acid. As mentioned, that acid did two jobs. Part of the job was to react with the calcium carbonate. That's what I need to know. And some of it reacted the next morning with the sodium hydroxide. What I'm going to do in the next slide is take a look at how much reacted with the sodium hydroxide. So, let's begin with the information that reacted with sodium hydroxide. And this is the equation for what went on. We determined the volume of NaOH required to neutralize 10 milliliters of the hydrochloric acid. That was done by a titration experiment. Changing that volume to decimeters cubed, I can then determine the number of moles of NaOH that I added. From this equation in the 1-to-1 ratio, I can determine then the number of moles of HCl that I added. Now, a little caution about this number of moles of HCl that was added here. It represents the amount that I added to a 10 milliliter sample. But remember that 100 milliliters was added. I only titrated 1/10 of it. So as a result, the actual number of moles of HCl that was remaining or in excess is 10 times that number. So I'll place that over here on the right. Now, with knowledge of the moles that I added and the moles that actually reacted with the NaOH, I can subtract those to determine the actual amount that reacted with the calcium carbonate, 0.0327. This is the number I need to return back to my original equation. So I needed to know the number of moles that actually reacted with the calcium carbonate. So back to my original equation, I want to determine the mass of calcium carbonate. Remember, all I know is it's less than 2.43 grams, and I know the molar mass of calcium carbonate. I now know the moles of hydrochloric acid that reacted with it. Employing the 2-to-1 ratio that exists here, I can actually determine now the moles of calcium carbonate. With knowledge of moles and molar mass, I can calculate the mass of calcium carbonate. Here I'm carrying one more significant digit than required because I'm not quite at the end. Now I'm going to take this mass and divide it by the original mass of my sample. And that then gives me the percentage of calcium carbonate in my original sample. Now I am making an assumption here that the other minerals did not react with my hydrochloric acid. Anyway, that brings us to the end of the stoichiometry unit. Thanks for watching, and remember, questions are always welcome.